All right, guys, I want to talk to you about torque. Now, we already know that for torque, we have an equation that will determine the magnitude of torque, such that the magnitude of a torque would be the r vector, the distance, the magnitude of the r vector, which would be the distance from the axis of rotation to where the force actually acts on an object. So we know Rf sine theta. And again, these would be the magnitudes of the r and f vectors. So for example, if we had a r vector, if this was our axis of rotation, and we have an r vector that would put us out in this region here, and we have a force vector that is acting like this, some angle theta. If we multiply the magnitude of r times f times the sine of this angle, that will tell us the magnitude of the torque. And then to find direction for this, how would we find the direction? Well, this is where we need to use our right-hand rule. So using the right-hand rule, in this application, you take your right hand in the direction of the r vector, curl your fingers in the direction of f, and the direction of your thumb means that this actually would be the direction out of the page or out of the screen coming at you, would be the direction of this torque. So magnitude and then right hand rule for direction. And really what we're talking about here is this sine theta is the perpendicular component of either this force or the lever arm. Okay? You can either use the perpendicular force vector, or we would use this distance here, which would be sine theta r. So it's giving you the perpendicular value here as it relates to these two vectors. Well, something that's new that we want to actually introduce here is this idea of the cross product. Okay, let me use a different color here. So let's go to red. And so we're going to use cross product. And what this will do for us, anytime you're doing a cross product of two different things, it tells you the perpendicular component of one vector with respect to the other. So for torque, if we were looking at torque, we could say that torque as a vector now, not just a magnitude, but torque as a vector would be equal to the r vector crossed by the force vector. And this is really helpful for us when we get into unit vector notation. When we're talking about in 3 dimensions, I mean, this is in a 2-dimensional plane, we can solve for the magnitude and use the right-hand rule. But if I wanted to track a 3-dimensional r vector with a 3-dimensional force vector, it gets really complicated to try and do that using Pythagorean's theorem in 3 dimensions and then applying the right-hand rule. It's just complicated. So this cross product will actually give us that actual magnitude and direction for the torque as it relates to this force and this r vector. So if we want to just start out by saying, well, let's look at how this cross product process works. Let me just say, let's say, so in unit vector notation here, we're going to say unit vector notation. Let's cross, there are 2 vectors, okay? Vector A and vector B. And A, we will say, has the 3 dimensions for unit vector notation. Say AX in the I hat plus AY in the J plus AZ in the K. And for B, we'll do the same thing. We'll say BX in the I plus BY in the J and BZ in the K. So if I want to cross these two, we'll actually use what's called a determinant matrix. Okay, and a determinant matrix, what that determinant matrix will look like, it will look like and will set up and shape up like this. So we're going to look at each the I, the J, and the K directions. and we will create a matrix for A and for B. So if I'm going to take these values here, the I component of the A vector would be AX. So I'm going to take AX, and then I have AY and AZ. I'm just dropping down the I, J, and K components of vector A. Vector B likewise would be BX, BY, and BZ. And this matrix will help us to actually calculate A cross B. Okay? So again, what are we trying to find? We're trying to find the perpendicular component of one with respect to the other in a three-dimensional aspect. And so what we first want to then find is, in the I direction, what part of B is perpendicular to A with respect to the I direction. And so how we're actually going to do that by using the determinant matrix here is that we're going to really cross out the I. If we're looking for the I, kind of cross out the I. And so we then come over here and we have this 2 by 2, and we will say in the I direction, if we look at what is perpendicular from B to A, we're going to say multiply AY times BZ and subtract AZ. So here's where we're getting this cross aspect, okay? AY times BZ minus AZ times BY. And that is the perpendicular component of A with respect to B in the I direction. And then we're going to add to that. We're going to look at now, move to the J. Now the J is a little bit tricky, okay? Because what you really have to do is move over another set of, let me use a different color here. Use this orange. So I'm just going to bring, you really want to bring the I column over here so it makes it a little bit easier for you. So I'm just going to put AX and BX here so you can get the same appreciation of what you're doing here. It was just like when I cover up the I have this little quadrant 2 by 2. If I cover up the J, you're going to really go AZ to BX, but I just wanted you to see this, okay? You can go, so we're going to go AZ to times BX. All right, here we are, AZ to BX. But if by bringing that over here, sometimes it's a little bit easier to help you guys to see this, AZ BX minus, then go over one more, AX BZ. AX BZ, we're running out of room here. This is for the J. Okay? Drop down here so you guys can see this. And again, you just go AZ to BX and then AX to BZ. And by moving it over here, you're just crossing here and you can see it's the same thing. Okay? Once you get comfortable with this, you don't necessarily have to draw this over here. It's just a way to make sure that you're crossing the correct ones. And then to find the K direction, it's just AX BY minus AY BX. So again, AX BY minus AY BX. And that is what is in the K direction. And so whatever this value is, that's the part of that is perpendicular within the I direction when you look at A cross B. So again, we're trying to find the perpendicular components, right? It goes back to this when we're looking at the sine value. That's going to give me my perpendicular component of the force or the moment arm, either way. And so this allows you to do it all in one shot using unit vector notation, and you can actually get a value that gives you all in one shot the magnitude and direction of the torque associated with a three-dimensional force on a three-dimensional vector. Okay, let's look at a problem example here. All right, so let's say that we have a R vector. Again, R meaning just the distance from the axis of rotation to where the force is acting on the system. So we have an r vector that is equal to 2.0 I minus 5.0 J minus 0.0 K, and this is in meters. And we have a force vector that is equal to 1.0 I minus 0.0 J plus 6.0 K hat. And this is in newtons. So here's our two vectors relative to the axis of rotation to determine the torque associated with these. All right, so we're going to determine the torque associated with these two. And so we're going to start out with the torque is equal to R cross F. By the way, this is not commutative. In other words, torque does not equal force cross R, okay? It's specific in the direction as it relates to R cross F. So these are not equal to each other. So just be mindful of that. This is not true, okay? These is not true. It's always R cross F to determine the torque. So let's set up the matrix. All right, so we have I, J, and K. And the R vector is going to be, so we have 2. Here we have -5 and 0. And for the force vector, the I, we're going to have 1. The J is 0. And the K is 6, positive 6. So R cross F, which is what the torque is, that's what we're looking for, is going to be equal to, again, let's go ahead and cross out the I. So we're looking at -5 times 6 minus 0 times 0 in the I, plus, we're going to cross out the J, and we're going to do 0 times 1. Again, if I wrote the 2 and the 1 over here, again, let me show you that just for those of you that want to do that way. 2 and the 1. Okay, I'm just carrying that over. So for J, we're going to do 0 times 1 minus 2 times 6. And that is in the J direction, plus, I'll write down here just to make sure we can see. So now I'm going to do the K, so you cover the K up, excuse me, cover the K, and I got 2 times 0, and minus -5 times 1 in the K. So let's sum that up. I have -30 minus 0. It will be -30 in the I, plus, let's see, we have 0 minus 2 times 6. So that's going to be a -12 in the J. And then in the K direction, we have 2 times 0, which is 0, minus a -5 times 1 is -5, so minus that. So this becomes a +5 in the K direction. And this is the torque, and we're measuring torque in Newton meters. And here is the actual torque magnitude and direction using the cross product to find torque.